So I understand that a lot of people that take organic chemistry are not chemistry majors, so I try to point out some interesting organic molecules and show you why functional groups are important. So for example, here I have serine. In serine, I have an amine over here, I have an alcohol up here, and I have a carboxylic acid over here. Serine is just one of the common amino acids that we have in our body. It's one of the building blocks for proteins. Here's another common chemical that you'll see every day, and that is glucose. In glucose, we have a whole bunch of alcohol groups. You see the OHs all over, and then we have something that's similar to an ether here in the ring. So in chapter 1, we talked about bonding, or what holds atoms in a molecule together. In this section, we're going to look at intermolecular forces. Another way to say it are forces that are between molecules. And these are going to help us to understand things about boiling points, melting points, solubility of different organic molecules. We'll start with ionic compounds. Ionic compounds have extremely strong electrostatic interactions. Throughout the material, from fully charged ions. These are much stronger than intermolecular forces are in covalent molecules. So ionic compounds are really held together strongly. They have very high melting points and boiling points, and only occasionally will we address those during class. What we mostly care about are covalent compounds. That's what we're going to see in most of organic chemistry. And in covalent compounds, there are 3 types of intermolecular forces. And I'll go through them in order from the weakest to the strongest. The first are van der Waals forces. And these are the weakest of all the forces. They exist in all molecules. They're caused by instantaneous dipoles. Which are in turn caused by momentary changes in electron density. And that's kind of a strange concept, so I think that it requires a little bit more explanation. If I look at a helium atom, I've got 2 electrons. Right? So if those 2 electrons are spinning around my helium atom, they are not always perfectly balanced like the way that I showed it here. We could have a time when both of the electrons are on the same side of the helium atom. If that happens, there's a negative charge developing on to the right side of the helium atom there, and a positive charge developing to the opposite side where the nucleus is with the 2 protons in it. So what happens then is if another helium atom comes nearby this one, and it has its 2 electrons, this electron will actually be pushed to the opposite side by the electron density of the other helium atom, causing an instantaneous dipole to be generated in the next helium atom. So anytime that this happens, it causes these 2 atoms then to be attracted to each other, as there's a negative towards this side of this atom and a positive towards the other side of the opposite atom. And that draws them together. So how can we tell what we're going to see for van der Waals forces? Well, if we have a larger surface area of the molecule, then there's going to be a larger attractive force, or larger van der Waals forces. And the reason for that is just simple. There are more atoms at the surface that have a chance to interact with one another. And more of them have an opportunity. The more atoms we have, the more that there's an opportunity that one of them or more will have an instantaneous dipole at any given time. And also, if we have a larger atom, larger atoms are more polarizable. That means that it's easier to push the electrons onto one side of the atom than another because the orbitals are larger. And so they have more easily induced dipoles, and therefore greater van der Waals forces.
The next type of intermolecular force is a dipole-dipole interaction. And dipole-dipole interactions are attractions between two polar molecules. And these are much stronger than van der Waals forces are. So for example, you could have something like an ether, and with an ether, and ethers have a delta minus on the oxygen and a delta plus on carbon. So because of that, if I bring another ether nearby, the oxygen from my second ether is attracted to the carbon from my first because I have a delta minus on this oxygen, and that's being attracted to this carbon. So it makes this intermolecular force between two molecules. And the third one is of particular interest to me, hydrogen bonding. I did my PhD thesis on low barrier hydrogen bonds within salicylate monoanions. So I've done some studying of hydrogen bonds in the past. Hydrogen bonds occur only when hydrogen is bonded to fluorine, oxygen, or nitrogen. And the reason why is that these are the most electronegative atoms. So because of that, the bonds between hydrogen and those three atoms are very polarized, which makes larger partial charges on each one, which lead to stronger intermolecular forces. And even as strong as these are, it's important to note they're still much weaker than covalent bonds. Calling them hydrogen bonds sometimes confuses people a little bit because they're not really bonds, they're still intermolecular forces.